of the specifications you'll find on a mixer datasheet, which will let us dig into how we evaluate mixer performance. I've thrown a mixer up here for reference, and it's in a down conversion configuration, so RF is our input frequency and IF is our output frequency. Arguably, the most important specification for a mixer is the conversion gain. This measures how much of the power at the RF frequency gets converted to the IF frequency. However, conversion gain is something of a misnomer because this gain is often less than 1, and it's guaranteed to be less than 1 in passive mixers. So, at least in this class, we're specifying gain as a negative number, indicating that you have less power at IF than you had at RF. You'll see other texts that talk about conversion loss in order to define it as a positive number. Isolation describes how much of the powerful LO signal leaks into other ports. This is an extremely important specification because LO appearing at other ports can cause a lot of mischief. LO on the RF port can re-radiate out of the antenna, and LO on the IF port can cause intermodulation with the IF signal. IIP2 and IIP3 describe the linearity of mixers just like they do with amplifiers. Passive mixers have very good linearity, and particularly IIP2, so they're popular in a lot of modern receivers. The noise figure of mixers is somewhat tricky, so we're going to give it another slide. To analyze the noise temperature of a mixer, we're going to imagine that we have noise with a temperature T1 at the input, which represents a combination of the input noise temperature and the contribution from the mixer itself. We're going to get two copies of the input noise spectrum at the output, one from the positive LO sinusoid and one from the negative LO sinusoid, and they're both going to be scaled by the conversion gain. Getting multiple copies of noise like this is called noise folding. The value of Tmix for a lossy mixer is 1 over L minus 1 times T, just like any other lossy passive. For an active mixer, it's going to be related to the noise factor, but you need to read the noise factors for mixers carefully, as we'll see on this slide. As a preliminary to that, I've calculated the input SNR of the input spectrum in the upper left. So if we calculate the signal-to-noise ratio at the output, we'll find that our SNR is degraded by both copies of the noise if we have a single desired RF signal for down conversion. This produces a noise factor that includes a factor of 2 in front of it. This noise factor is called the single sideband noise factor, and it's widely used by RF designers. Another definition of noise factor presumes that we have desirable signal at both omega LO and plus omega RF, and omega LO minus omega RF, which is what we saw in our kind of naive upconversion example in an earlier video. This doubles our signal power at the output because both copies land at the same place in the IF signal, so as a result our noise factor is halved. This is called the double sideband noise factor. Finally, the IEEE has a third definition of noise figure, which doesn't penalize mixers for having two sidebands. It filters the noise out from one of the two sidebands by assuming there's a very narrow bandpass filter around our signal. Suffice to say, I think it's easiest to think about the noise temperature at the output of a mixer rather than dabbling in the noise figure. So keep that in mind. So in summary, the conversion gain is the power at IF over the power at RF. The isolation from LO to RF is the power at RF divided by the power in the local oscillator. The isolation from LO to IF is the power in IF divided by the power of the local oscillator. IIP2 and IIP3 are the same in mixers as they are in amplifiers, and IIP2 is important in direct down conversion. And mixers capture noise temperature from both the desired band and the image, which leads to multiple possible noise figure definitions.